Hello, welcome to Lab 6. My name is Ryan Martin. My lab partners are Chong Ting, Daniel Pebbles, and Robert Urban. So Lab 6 is called Subroutine Parameters and Returns, and the objective of Lab 6 is to learn how to pass arguments or parameters into assembly functions, return values from those assembly functions, and how to implement parameters and returns with recursive functions. Okay, so now there are two methods of passing arguments into assembly functions. The first method, and the method that we'll go over the most in this lab, is on the stack. The second method is by using your registers. Now the method of passing arguments on the stack is the default method by your GCC compiler, but it's far less efficient than using the registers. It's simply used by default, though, because it makes the argument passing algorithm much easier to implement. In order to pass your arguments in the correct way, there needs to be an agreement between your caller and your callee functions. For example, if you're using the stack, how is the callee function going to know in what order to retrieve the arguments from the caller function? So the method that we use is known as the LIFO method, and that stands for last in, first out. Best way to remember that is just reverse order. When you're passing your arguments on the stack in assembly code, you want to pass them in reverse order. So for example, we can take a look at this C code. Let's say we have some function that returns an integer value. We can call it myfunc. And let's say that it has integer valued arguments. Call them x and y. Now, the one thing to note here is that x is your first argument, so we can denote it saying, say, R1, and y is your second, R2. Now, if we wanted to put this into assembly, we would have to remember that R2 is what we want to be pushing on the stack first. So, in order to pass them in reverse order, we might say something like this. We want to move whatever argument it is, whatever it may be, and this isn't necessarily the exact code that you would use. This is simply to illustrate the reverse order point of how you pass in your parameters. So just say any R2, whatever it may be, into one of your registers. Let's pass this one into the B register. Then you pass the first argument. We'll put that in the C register. And if there were 3 arguments, it would be all the same, except above the second argument, you're still going to have your last parameter passed in or pushed onto the stack first. So, or not push on the stack, but you want to use your arguments in reverse order this way. When you push them onto the stack, like so, you know that first you're going to push in your B register, say. So B push your B register. push your C register. Now, the reason for this order is because if you move your last parameter into the registers in that order, then you can simply push the registers in the order that you've already written, so it makes it a little easier to understand that. Now that we've pushed our registers containing the arguments onto the stack, we now are ready to call our function. So now at this point, the code will jump down and say, down here, to the myfunc label. And it'll execute whatever is within the function, and then once the function is returned, it'll jump back up here, and at this point, we need to add to the stack pointer in order to restore the space used up by our two arguments. And since our arguments are both integer valued, they both take up 4 bytes, we need to add 8 to our stack pointer. And for example, if we had 3 arguments, we would need to add 12 to the stack pointer. It's simply restoring the space that was taken up by our arguments because we no longer, the caller function does not care about the arguments in the callee function, and now it's ready to execute whatever code is going to, whatever is going to be after this part of the code. You'll be asking yourself, from Lab 5, you might remember that for every push, there needs to be a corresponding pop. But if you recall what the pop instruction is, it reads the value at the current location of the stack pointer and then increments the stack pointer. By writing this instruction here, adding 8 to the stack pointer, we can increment the stack pointer back to wherever it was before we pushed any number of arguments. And because there are 2 arguments of 4 bytes each, we increment the stack pointer 8 bytes. We've called our function. We're ready to move into the function. And so the question to be asked is, how does our callee function retrieve the arguments that we pushed in? So to illustrate this, let's go ahead and fill the stack up with what we've done so far. So whatever is in this bottom address was, whatever was maybe in the stack previously, irrelevant. And for the purpose of this example, we can say, let's just say the value of R2. Let's say there's a value of 5 in R2. And R1, maybe we can make it 10. So, the first thing that we've done here is we've pushed the value of R2, which is stored in our B register, which is 5, on the stack. So first off, at the bottom here, first thing pushed in is 5. Secondly, we push the value stored in the C register, which is R1, which is 10. And then the call function is going to also push our return address from myfunc. Excuse me. So now we can move, so this is going to go, with whatever code, maybe here, going to reach the label myfunc, which is right there. So now we are ready to write the prologue of the function. So we can write prologue. Now first, we push So, as I said, the callee receives parameters based on two things. First, the prologue of the function, and secondly, the number of arguments passed into the function. So for this prologue, let's push we'll save 3 registers. Saving 3 registers to the stack for use, or for, pushing 3 registers, or saving 3 registers for use in the function. So we can say whatever address is pointed to by the base pointer, let's call it, say, 0, 1030. And then we can say EDI, say it's 15. Push EDI 15, EDX say 25. Whatever may be stored in those registers before we change them, if at all. Okay, so after saving those 3 registers, we now move stack pointer base pointer. So what this is doing is, since what's stored in the stack pointer here is whatever address is pointed to by that stack pointer, by moving it to EBP, we're storing the address that is pointed to by the stack pointer into EBP. So at this point, say EBP is now pointing at the top of where we are at, because each time you push an argument, in, the stack pointer is decremented with each push. So now, by moving the location that the stack pointer points to into the base pointer, now the base pointer is pointing right here. And then, since retrieving the functions, or retrieving the parameters also depends on the prologue, that's somewhat based on how much space you allocate for local variables. So in this example, we're subtracting 12 from our stack pointer. So by doing that, we are allocating space for 3 local variables in my func. So now our ESP will be pointing at 12 bytes above. So it would be 1, 2, 3. Now our stack pointer is pointing here.
So how does the stack pointer works? Like, how does it move?
Okay, I can explain it a little bit more. Starting at this first instruction here, before any of this takes place, our stack pointer is going to be pointing at at whatever location before we push any registers. And by pushing our register B and our register C, which is this and this respectively, our stack pointer is going to change with each instruction. So, for example, let's say let's denote this 1. For 1, now it's pointing here. For 2, now it's pointing here. Because with each push instruction, the stack pointer is decremented in order to be pointing at the top of the stack. So, And so likewise for the call, since it's pushing the return address, now it's pointing here. So now since we're going into the function, we're pushing our base pointer, which is this arbitrary address down here, which may be whatever the base pointer is pointing at. But since it's a push instruction, once again, 4, now it's pointing here. And likewise for these two, 5 and 6, once again is pushing or moving the stack pointer up the stack with each push. So then after this, since the stack pointer holds a location that is pointed at on the stack, by moving that location into the base pointer, it's changing the location that the base pointer is pointing at and moving the location that is stored in the stack pointer to also be pointed at by the base pointer. So that's the reason that the base pointer is now, since this is currently at the end of this instruction, the instruction say number 6 here, since it's now pointing at this 0x100C, by moving that location into the base pointer now, the base pointer is also pointing at this same address. And then, so that's taking care of that instruction. And then now by subtracting 12 from the stack pointer, with each cell here, or each block, taking up 4 bytes, 12 divided by 4 is 3, so it's going to move 3, 2, or 1, 2, 3 blocks up, and now, finally, the ESP is pointing at here. And this is to simply allocate space for 3 local variables within your function on the stack. So now, if you understand that, you're ready to understand how the callee is actually going to retrieve the arguments now that we've completed the prologue. Now we're ready to retrieve our arguments. So since I mentioned that retrieving the arguments is based on 2 things, the prologue and how many variables are passed in, hopefully you can see how the number of registers as well as the number of local variables that you allocate space for on the stack can influence where your base pointer and your stack pointer are pointing to in relation to your R2 and your R1. So this is where the last in, first out principle applies. You can now understand, or you can now see how this is the first argument and this is the second argument. So the way that we're going to retrieve our arguments is by using an offset, using register indirect addressing. So all right. So, since we're adding an offset to our base pointer, which, if you recall, is now pointing at this location, 100C, all we need to do is find how many bytes offset from this location pointed to by the base pointer is our first argument, or our second argument, or sorry, our first argument and our second argument. And if we can count them, just 4, 8, 12, 16. So that means our first argument to be retrieved by the callee function is 16 bytes away from our base pointer. So we can add a positive offset . filling in this blank will be the number, or the number of bytes offset from this base pointer to get there. So as we just said, 16 to retrieve that first argument. And just simply one more box away would be 20, since each one takes up 4 bytes. So now, in implementing these two instructions, we've moved the value pointed to in 16 bytes above the base pointer. So remember, the stack is oriented in an opposite manner. So by adding an offset, you're going down the stack. I mean, I guess you could move a. Never mind. So by adding 16, or making an offset of 16 from this location pointed to by the base pointer, you retrieve this argument, which is our first argument, and this argument, 20, which is our second argument. So that illustrates why the last in, first out principle is necessary in order to pass parameters using the stack. Okay, so after the callee function has retrieved the arguments from the stack, it can then execute whatever may be written in the function, and then the epilogue will essentially do the opposite of what happened in the prologue. The epilogue will pop the registers that were pushed in the prologue, as well as restore the space allocated previously in the prologue for the local variables in the callee function. So, and then after this takes place, it'll now return to after the call. And if you recall from the previous portion of this lab video, there's the instruction to add 8 to your stack pointer. And just as the epilogue restores the space allocated in the prologue for the local variables, this instruction restores the space allocated for the variables that were called before the call of the function, aka these two integer valued, 4 bytes each, 8 bytes total, these two arguments that were allocated space for in the caller function. So now that we have restored the space for the local variables of the callee function in the epilogue, as well as the variables in the caller function right here, we are now complete. We've now covered all our bases as far as popping the registers and all of that, and that concludes this example. However, one thing to note is I've used the B and C register, and although it is up to the programmer's choice, I use those registers because, as it might be going over later in the lab, but whenever you're returning values from your function, you always you store them in the A register to be returned. So that's why I did this, just to illustrate that point of that the A register should be saved for whatever value you're returning from your function. So that concludes the introduction to Lab 6, and my lab partner Chong will be going through a little more complicated example for you in the next video.
Okay, this is an example for Lab 6. Here we have an example of a C code function, 2 functions. Function 1 will be the caller, and function 2 will be the callee. And this is notice that this is not the main function. So what we're going to assume is that the BP and the ESP will be in a higher stack address value. So let's just say 5C, 15C, right? So basically they're pointing to that value down there, right? Before we doing function 1. Then when they're calling function 1, we have to set the EBP and ESP to begin declaring the variable for these 3 variables. So the first thing we do is to push using the command push. Then we push EBP, and this will move the pointer to 134. And then we also do move ESP to where EBP is. So basically, these 2 command line will move EBP first to 134, and then that's the push EBP. Then the move ESP to EBP is the same thing. We move to this address, and this will be the return address once we come down to here. So EBP and ESP address value will be 134. Okay. Next, we have to declare the amount of space that we need for our local variable. Here we have 3 variables, x, y, and z, and each one of them are int data type, which is 4 bytes. So to declare the enough space for it, we use subtract function, the subtract command, and subtract 12 from ESP. This will make the ESP pointer, this one, move up to 128, because that's 1 for the x value. This second one, which is 8, which is for the y variable, and 128 is for the z variable. So 134 becomes 128. Next is the 8 equals x line. So we have to store the value of 8 to x. So this can be done using the move command. Move L, $8, -4, parentheses, EBP. This will act as the -4 EBP will move the base pointer. Basically it will move the address to subtracted by 4. So instead of doing another subtract EBP, we can just do -4 parentheses EBP, which is the pointer kind that we learned in lab 4. So this will make 130 have the value 8 for the x variables. Next, 2, y equals 2. So we do the same thing that we did to x. which is move $2. And this time we have to do it by -8 because y is 8 bytes offset from where EBP is. So it'll be -8% EBP. So this will make where the address 12C had the value 2 in it. As you can see, that we did not change EBP because EBP is inside parentheses, just basically addressing where to store these values to. Next, it will be calling this function, and then the return value of this function will be stored into Z. So, first thing we need to do is to push anything that is valuable that we need. Let's just assume if we have something valuable in register A. So basically, you would do is push register A. Then it will store the value in register A. And every time you push, it will increment the value. It will increment the ESP to here. And then whatever is in register A, for example, let's say -9 was in register A. And then here it will be storing register A in there. Next, we have to pass in the arguments into the function, and we have to do it from the last argument backward to go in. So the first one, which is to do that, use push L hashtag R $-1. This will increment again every time you push. Will increment the ESP or decrement the ESP up to 120, and then -1 will be stored here. Then after that, we do y. Since y is a variable, we have to, we cannot store a register. We can't store. We can't do we can't push two things at once. So basically, we need to move the variables to a register. So first thing we do is move the y variable, which is -8 EBP, to a register that we know. So for example, I'll be using register C. Then after that, you push register C to save it. So whatever value register C is, it will be saved on the next step, which is 1C here, which is 2. For X, we do the same thing that we did for Y. So we have to move -4% EBP, which is a variable that we store 8 into X. So we put the variable Y, the variable X into, let's just say, we can use the same register again if you want, because we already saved it on the other one. So we can still use the same register to store the X, the value for X. So and push. So basically, this ECX and this ECX is two different things. First one is for at the address 11C. The second time you use it, it will be at 118. So the value for this one will be 8. And the stack pointer will be 3. Now that we have pushed all the arguments that we need for function 2, the next step will be calling function 2. Next, we will be calling function 2. So here, from here on, I'll be erasing all of this and have enough space to do function 2. So after this, so once you call function 2, we had to do the prologue for function 2. So basically, what we did in the beginning for function 1, we do push %EBP, which means that this EBP value will now be moving. Okay, so before I push, I should have, because the caller function will increment the ESP up to 114. So this right here, ESP, when the call function is called, it will return back to function 1. And then after that, push EBP will be next, and then it will increment it and store the address that EBP was from 134 to here. So the address of 110 have the address 134. So this has become 110. And this is here, it will be 114. Next, we will move ESP to where EBP is. So move ESP to EBP. This will move this pointer to where EBP is. Now, the next step is to declare a space enough for the one variable function 2 have. So this will be subtract $4 for percent ESP, which will move the ESP to 10C. Next, we have to do the arithmetic here. And to do that, we have to fetch the variable a from using the EVP, because there is no label for the variables in the function 2. And to do that, we do move 8% EVP to a register that we can use, which is the A, B, C, or D register. And for this case, I'll be using C. And then next step, it will be adding the variable B to A. So it will be 12, 0, E, P, and storing it into the register C. Why am I using 8 and 12 to offset EVP? Because EVP is right here where 110 is. 8 from EVP is where variable A is for function 2. And then 12 binds off from EVP, which is where B is for function 2. So for the next value to add C into it, it will be 1, 2, 3, 4. So 4 times 4 will be 16. So we add 16 EVP to register C. And then register C will have value in it. So now we can now move all the sum of these three values into the local value x. So using this command, move the value in register C to the local variable x, which is -4%. So -4 EVP will move it to here. So storing whatever values and C into here. So this will be 9. Now we have the sum. After we do that, after we do the arithmetic, the next part is to returning the value in x. And to do that, we have to return it in the register A. So first thing, we have to move the local variable to register A. So move -4. So this will change the value here to 9, but it does not change the order value of register A to 9, because it will be storing here, not where the stack is. So the next thing to do is to move EBP to ESP and then pop EBP. So it'll be move, because wherever we were doing the last in, first out structure. So what we did was moving, subtracting ESP. Now we're adding ESP, kind of like a shortcut of adding ESP to EBP. So we move percent EBP to percent ESP. And then we pop it to go back to the return function, and it will so this, well, move EBP back down to 134, and then ESP will return back to 114. Now that we got registered, now that we are returning back to function 1, our next step will be the next step will be the command under here. But we have to store the value that we returned from function 2 to the variable z. And the value that we returned from function 2 is in register A. So we have to store that in the variable z of function 1. So after all that, we had to move the values in register A to the variable of function 1 z, which is negative 12% EBP. So basically, EBP is here after we popped it, and 12 from EBP will be here. So this will have none in it. Then the next step is to add 12 to percent ESP, and which will move ESP down to here. And then we pump the register EAX to return Z back to the function, function before function 1. And that concludes for example from lab 6.
Alright, for our example, we are presenting how to pass an array into a function. This is a very general C code we devised to simply give it as an example. On the right side you'll see the function, on the left side you'll see the function prior to the function on the right. On the left side we have an array being declared with 3 elements. Each of the 3 elements are then assigned a value. Then a second integer value is made for the size of the array. In the actual function, what we are going to be doing is passing a pointer to the base of the array, along with an integer that contains the size of the array, as shown by the size of int a over here. At the end of this function, we are going to be returning the value that comes from the function here. And onwards to the function itself. The function is very simple. It's simply a loop that's going to be adding each value of the array up. Very simple. Returns it. The main thing to pay attention to is, as we know in ASM, the first in, last out rule. The integer value of how many elements are in the array is what's going to be transferred to the stack first, as opposed to the base of the array. Labs, there's always been a prologue which up until now didn't make much sense to us. Bear in mind, the first part of our stack, which as we know works its way up while going down in addresses, is going to be the return address of the function that we've already been in, myfunc, from previously. The first part of our prologue is going to be pushing EBP, the base pointer, making that the next item on our stack, which is currently going to be where the stack pointer is pointing to, and we are then going to be moving the value, the address of the stack pointer, this location, into the base pointer, making the base pointer point here as well. We are going to be leaving the base pointer here to act as a reference for following declarations and such. We are then going to subtract 12 bytes from ESP, the stack pointer, which in a sense moves it up 3 locations because each integer takes up 4 bytes of space. So the stack pointer will currently be located right here. We are then going to move in descending order -4 from EBP, the base pointer, so up 1 spot, and we're going to put the value of 1 in there, as we did in our array declarations. Then we're going to do 3 into the second one up, and then 8 into the third one up, as is obvious by a 12. After that, we are going to move the base pointer into the A register. So the A register will contain the address of the base pointer. Afterwards, we will subtract the stack pointer's address from the A register, which is actually going to give us the difference between here and here. That is, of course, going to be 12 bytes. So the A register will then simply contain the number 12. After having that, we are going to divide the value of 12 by 4 in order to acquire the actual number of elements in the array, which is 3. Now, for later purposes in the sum array function itself, when we're doing jumps, we are going to subtract 1 from it to give us a 2, and then we are going to multiply that value by -1 to give us a -2. Because, as you've seen here, we have to use negative offsets when working, because we work from the base pointer as opposed to the stack pointer, which would make them positive offsets. It's simply the way to do it. Alternatively, you could work from the stack pointer, but it's not the correct way to do it. After that, we're then going to move the value of the base pointer into the C register. This is going to be working on obtaining the base of the array to be passed to the function. We will then subtract 4 bytes from the C register, which contains the base pointer register. So in a sense, what we're doing is by subtracting 4 bytes, what we're putting in there is then going to be the address of the first element of the array, which is the goal, to have the C register have the value of basically the pointer to the first element of the array. So you could write BP minus 1. We then push EAX because first in, last out, it is the number of integers, or the number of elements in the array. So we are pushing -2 onto the stack first, and then we push ECX. This gives us BP minus 1's address. We then call SumArray, and when we call a function, what we're actually doing is pushing the instruction pointer and then decrementing the stack. Or decrementing the stack and then moving the instruction pointer, which is going to put the return address here for the next function that we're jumping to, which is over here. Left off. We are currently have the stack pointer located at the return address, because we've just started the sum array. We're at the jump location for the function. The first thing we do, as usual, is we push the base pointer. So the base pointer will then be the next item on our stack. And that's where our stack pointer will be located. And then the next thing, as usual, is we move the stack pointer into the base pointer so that the base pointer is located at the location of the stack pointer as well. So they are both pointing to the base pointer at the top of the stack. Next up, we're going to, just for the sake of clarity, seeing as how we declared the function x and set it equal to 0, and that's what we were using the sum into, we're going to declare another local variable by taking 4 bytes off the stack and incrementing the stack pointer in doing so. So the stack pointer is going up here, and we're moving a 0 into that value, which we use in direct referencing for. The next, we're going to be moving a 0 into EDX to clear it in the case of something already being in there, say from previous division or the like. Next, we use the base pointer and an offset with indirect referencing to move the value of, if you were to look from the base pointer, you'd go 1, 2, 3 times 4, and that would give you the 12. To explain how that works, this is moving the value of how many integers or how many elements of the array there are into the value of EAX register, which is already there. We already have it left in there because we didn't push any, well, we pushed the register, but we didn't clear it. And as you know, when you push or you move something, the computer doesn't delete it because that would be less efficient. They don't go back and do that. They just move something, copy it over, and then it's left to be overwritten. Then you go move down 8 bytes from the base pointer address, as seen here, to get the address of the base of the array, which is completely dependent upon the address given from the address that was pushed. This could work. This is why it could work for any number of elements, not just specifically hard-coded. It's what makes this actually a viable function. It is moved into the ECX where it already happens to be, or it's overridden in this sense, and then we begin the loop, where we start with it called the jump is called sum, and we use indirect based indexed addressing to loop, to use the base of ECX, which is the base of the array. We are adding the offset, the value. This value here is the offset that gets the number of offsets that gets multiplied by this value, which is 4 because we are dealing with integers. So in this first case, you're going to have -2 multiplied by 4 to give you a -8 offset for the ECX's address. And as we know, the ECX is going to be pointing right here. So the first value is going to be 8. 8 for each, makes sense. So we're moving the value of 8 into EDX. Instead of that 0, we will then have 8. We then proceed to add a 1 to the A register, which will bring that -2 down to a -1, or rather I should say up. It then compares 1 against the value of the A register. So you're basically saying -1 minus 1, which will give you -2. And then if it is not equal to 0, as J and E means, it'll just jump back to sum. And because -2 is not equal to 0, you jump back to sum. We go through the process again, where this time it's going to be -1 times 4, so it's -4 from the ECX address, which would give you the 3. That 3 is added to the EDX, which gives you an 11 in here. You add 1, which is then going to give you 0. You compare 0 minus 1 is still -1, which is still going to cause it to jump because it is not equal to 0. It goes through it again. You have a 0 for the offset. You're just going to have basically the value at the base of the array, the first element added, which is a 1. So it's going to change this value to a 12. Then you add 1, and that's going to give it a value of 1 in the A register. Then when you compare 1 against 1, 1 minus 1 is 0, so it doesn't jump. This then causes basically the end of the summing of the function. So for clarity though, because we wanted to make use of that local variable, we moved the value in EDX, which is the sum of the entire array, back into the indirectly referenced stack pointer, which is up here. And so that'll give us the 12 up there. Now, as we know, when we're trying to return an address from a function, or to return a value from a function, we need the value that is returned will be returned from the A register. So we'll move the value that is at the stack pointer into the A register, thereby overriding what was previously in there. We then move the base pointer to the stack pointer. Now, by doing that, what we are doing is actually moving the stack pointer down to the location of the base pointer, completely ignoring the top value of the stack because it doesn't matter to us anymore. So we then pop EBP, the base pointer. So no longer is BP on the stack pointer gets decremented to the return address, and then because the return address is at the top of the stack, we then return. That takes return address off the top of the stack, and stack pointer is automatically incremented, sending the stack pointer back to the top of the to the stack of the previous function, where we then go on to the epilogue, which comes after the function call. After the function is called, we add 8 to the stack pointer. By doing this, we are basically skipping over the values that we push, the ECX and the EAX, because they're no longer relevant. So the stack pointer will now be here at the end of our array. We then move the base pointer to the stack pointer. By doing that, it basically takes the stack pointer and moves it to the bottom where the base pointer is. Then we pop the base pointer, incrementing the stack again to the return address of the my func. And then we return, which takes this function and finishes it, sends it back to wherever it was in the code. Now, an alternative to what we could have done instead of this is we could have also just added, say, 20 and went all the way from where we were here, 1, 2, 3, 4, 5. And that would have taken us to the base pointer where we could have just popped it, then returned and been done. Or we could have been fancy and popped both ECEX and EAX if we had wanted to keep it. All right.
Hi, for this example, we're going to be taking C code and we're going to be translating it into assembly. We have ivar2 equals myfunc, gvar, comma, ivar, and then some code that really doesn't matter, and then int myfunc, int A, int B, and we're going to be returning A over B. Something to keep in mind that's important is that there is already important data stored in the A register. Part, like I said, the caller has data in the A register, so we're going to have to push the A register, and ivar is a local variable, so it's 4 bytes from the base pointer, and we're going to move it into the B register. Then we're going to push the B register, and gvar is a global variable, so we can use direct addressing, which you see right here. We're moving gvar into the B register, and then we're going to push the B register. Then we're going to save the instruction pointer to the stack and set the instruction pointer to the first instruction of myfunc, and then we're going to call myfunc. Always retrieve the return value from the A register, and since ivar2 is the second local variable, it is offset by 8 bytes from the base pointer. And then we're going to move the A register 8 bits away from the base pointer. And since arguments are temporary, we don't need to pop them off, but we do have to manually increment the stack pointer. So we're going to add 8 back to the stack pointer to offset the 8 bytes. Then we're going to restore the A register, and by popping the A register. Assembly function from earlier. Now for our function, myfunc, our parameters are int A and int B, and our return will be the quotient of A over B. You're going to want to put this in the header of your function. For time's sake, I didn't put that. And then for the prologue, there are 3 local variables, so we will need to save the base pointer register, and that's what we're doing here. That's why we're pushing the base pointer register. Division is going to require the A and D registers. We can use the A, C, or D registers without having to push them. Now we need to get space for the local variables, so we're going to move ESP into EBP, and then we're going to subtract 12 from ESP. And then we have to clear the D register for division, so we're going to put 0 in the D register in order for there to be a 0 in the D register to make sure. And then we're going to set the dividend in the A register by moving 8 bits from the base pointer into the A register. By dividing by the divisor, right here, and the quotient is saved into the A register, which is great because that happens to be what we returned. Now for the epilogue, we restore the last space claimed on the stack by the prologue. We have 12 bytes for local variables, so we need to undo that. We're going to move the base pointer register into the ESP, and then now the stack pointer is referencing the address we saved the base pointer, where we saved the base pointer, and then we're going to pop EBP, the base pointer. There's nothing else to pop off the stack, so we will return. So return will read the return address set by the call from the top of the stack. It will save this address in the instruction pointer register, so that the next instruction to be fetched will be the one at the return address within the caller function, and that's what return is going to give us.